Hi everybody. So today's lesson is going to be all about the natural log and exponential base e. So there is a base e that is a number. So if we have an exponential expression that's e to the x, e is approximately 2.72, which needs to be known for an essay quiz. But anyway, e is an irrational number. And it can be found on a calculator. So if you actually look at your calculator above the ln, usually you'll see an e to the x. Oops, sorry. And you can see there's a decimal here. If I type in e to the first power, which is just e, it's 2.718 blah, 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 blah. If you want to memorize those, feel free to do that. But 2.71828 This is actually a repeating decimal, or a non-repeating decimal, so then it is an irrational number. If we're talking about the graph of y equals e to the x power, then we can talk about the domain and range. So if we're talking about the domain of y equals e to the x power, same thing as any exponential function. We could plug in any x that we want. And if we had a table of x and y values, let's plug in -1, 0, 1, and 2. If we were to plug into e to the x power, we would get e to the negative first power, which is equal to 1 over e, which is 1 over 2.72, which is 0.37. So if I were to go -1 and 0.37, 0, e to the 0th power is 1, because anything to the 0th power is 1. So I'm going to plot that dot. E to the first power is 2.72, like we just talked about. So 1, 2.72. We'll have to guesstimate where that goes a little bit. And then e to the second power is whatever 2.72 squared is, which is, looks like 7.39. So 2, and then a little bigger than 7. So this looks just like the exponential growth that we talked about in section 7.1. And remember that we talked about, if we're talking about the inverse of that equation, the inverse of the logarithmic equation is called a natural logarithm. And it's abbreviated as ln in your calculator. And the natural logarithmic function, the family function, is just y equals the natural log of x, so ln of x. If we were to plug this in, though, if you recall, since the natural log and e to the x power are inverses, we could just switch x and y, right? So really what you're doing is, if you had, let's say, -1, I don't know what the natural log of -1 is off my head, right? But we do know that e to the negative first power is 0.37, so if we had 0.37, we could get a y value of -1. We know these are inverses, so when my y value is 1, e to the 0th power gives me 1, right? And then we're sort of just flip-flopping these values, right? So e, which is 2.72, right? So we're plugging in e into our equation, and then we're going to get out these values that we already talked about, right? So really, if we have 7.39 comma 2, let's just put that here. And then I have 2.72 comma 1, 1 comma 0, and then, what was it? 0.37, -1. Oops. If you look at this graph, though, these 4 points, these are still a reflection about that line y equals x. So these same rules apply for inverses with exponential and logarithmic functions. This is just special because the base is some irrational number e, and then the natural log is just special because it's using base e. But essentially it's the same thing. If you recall, though, the domain and the range for y equals e to the x, it's going to be just like what we talked about for exponential functions. Our domain could be all real numbers, so anything from -infinity to infinity. And then the range here, remember how it approaches 0 but never gets there. That means it has an asymptote at 0, and then it approaches infinity. If we're talking about the domain and range for the natural log, it's just the inverse of that. We're going to switch the domain and range. So here, my x values, oopsies, should start at 0. I should fix that. It should start at 0, never touch 0, and then approach infinity. And then the y values can be below or above that x-axis. So for the natural log, the range values go from -infinity to infinity, right? So once you have this idea of these are basically the same thing, just fancy. So since e and the natural log are inverses, some fun things happen. So if we have the natural log of e, this is saying e to what power gives me e? Well, e to the first power would give me e, right? On that same basis, what's the natural log of 1? Well, remember, if there's no base here, it's the natural log automatically has base e. So e to what power would give me 1? Well, that would be 0. And then the natural log of 0, e to what power gives me 0? Well, remember, that's not possible. So this is a way of saying no solutions. That 0 with the x through it, right? 0 with a line through it. There is no way for you to get 0. Think about it. There's an asymptote at 0, right? So you'll never actually touch 0. So once again, the natural log of 0 is no solutions. You will need to know these for an essay quiz as well. Okay, so we're going to do some practice simplifying. If you recall from before, if we had the log with the same base as what we have here, we can cancel these and we're left with just our exponent. This is using that rule from 7.4, right? So just like if we had log base 3 of 3 to the 0.15t, log base 3 and the 3 would cancel and we would just be left with that 0.15t. Same rule applies for natural logs. So this question's a little tricky. If you have e to the 3 natural log of x plus 1, you need to get that 3 out of the way because it's sitting between the things that would cancel. So right now, if I move that back into an exponent, now I have my e and my natural log next to each other. They would cancel, and I'm just left with x plus 1 to the 3rd power. Similar rules apply for natural logs as logs. In order to combine logs, addition means to multiply. So I'm going to have the natural log of e to the 2x times e to the x. And if we're multiplying exponential expressions, we add those exponents. So I would have the natural log of e to the 3x. And oh look, I have a natural log and an e right next to each other. Those would cancel, so my answer is just 3x. Just to repeat again, natural log and e cancel each other out when they're right next to each other, so my answer is just 3.2 here. Those are inverse operations, so they would cancel each other. B, my inverse operations are not directly next to each other, so we need to move that 2 back. And then I can cancel my inverse operations to be left with x squared. And then this last guy, I have natural log and e. My inverse is right next to each other, so my answer should just be x plus 4y. Another thing we need to talk about that involves e, base e, is this formula APERT. It's the formula for compound interest. So the idea is that it is continuously compounded. The idea is that it's collecting interest forever and ever and ever at all times. So that is important. And yeah, if we're looking at APERT, A is the total amount, which sort of makes sense. P is the principal. This is the money that you start with. Right? The principal is the money that you start with. I think about this as you start your day by looking at the principal, right? Because you have to see Mr. Simmons when you walk in the door. So this is the starting amount. R is the annual interest rate. Make sure that you write the percent as a decimal. And then T is the time in years. And then just a reminder, E is approximately 2.72, right? So that's just a number. So if we have an example of using a PERT, it says, what is the total amount for an investment? So we're looking for A. So if we start with $500 invested, that would be my P. My interest rate is 5.25%, which converts, if I move the decimal back twice, to 0.0525. And then my T is equal to 40. So if we were to plug all of this in, my starting amount is 500. E is 2.7 or 2.72, and then we're going to plug in 0.0525 and 40. So once again, if we were to plug this in, I have 500E. If you have a graphing calculator, it's right above the natural log. You'll look for an e to the x power. E to the, and then in this case I'm going to use parentheses because there's two operations here, 0.0525 times 40 power. So hopefully that works, or you can see that-ish. It's super blurry, sorry. But I just plugged in what I had in my equation, and I get my answer of how much is in my account after 40 years, and I got lots of money. I have $4,083.08. And then that's it. However, we could do the same thing again with this example. It's the same thing though, so you can try this on your own. We do need to talk about half-life though. Half-life is sort of the opposite. It looks fancy. It's the process of how long it takes for a substance to decay or break down over time. And natural decay has a function that's written below. So N of T is how much is remaining at time T, right? This N sub 0 is the initial amount, so when time is 0, so that 0 sort of makes sense. Remember, E is 2.72. K is the decay constant, and T is time. Notice how there's a negative there, so just be aware of that, right? So if we are going to do this question, step 1 is to find the decay constant, so half-life. So determine how long it will take for 650 milligrams of a sample, which has a half-life of 28 days, to decay to 200 milligrams. So remember, half-life means what's half of my initial amount, or whoops, what's half of 650, how long to get cut in half. So we're looking for how long it takes for this function to be cut in half, which means it should be at 325 milligrams. And it started at 650, right? And then I have to look for this constant. And remember, the time it took for half-life was 28 days, so I'm going to plug in that 28. Right? In order to solve for K, I need to move the 650 out of the way first. So I should get half, which makes sense, equals e to the negative k times 28. Remember, to undo an exponential, we have to log, but in this case, we're going to be natural logging both sides. We would get the natural log of 0.5 is equal to, in this case, natural log and e cancel, negative k times 28. And then I would divide by 28, negative 28, to get my answer for k. So once you have this constant, this is your general equation, and typically you're given an amount you want to figure out how long it takes you to get to. So now I can solve for time the same way I had to solve for k above when I was given time. And you should get 47.5.